Okay, so last week we had discussed EM waves through conductors and dielectrics. Today we will see how power is transferred through EM waves by proving something called the Poynting vector. Note the spelling. It's not point I, it's Y, named after the scientist who first devised it. Okay. So what does Poynting vector say? We have to prove this first. We start with we assume that mu equal to mu naught, mu r, and epsilon equal to epsilon naught. Can we write this? Can we write this? So is it okay?
Yes, sir.
Now we use one result, that is this is from vector identity, right? And if you see that we have already calculated this and this, so we can replace. Sorry. Is it okay? Is it okay? We have just replaced this and this from the by these two equations. So we can write this. So look here carefully. What is this? This is can be written as okay. Then we can invoke the product rule of differentiation. So this will be right. That is equal to. Is it okay? We can write that similarly. We can write are they okay? Are they okay? Can we write them as this way? This way? This is fine. Okay. So we can replace this and this by we can is it okay to write this? Sorry. Is it okay to write this?
minus j dot e or plus j dot e?
What was that here? Minus was there? Minus or plus? Minus, right? Same as here. I want to replace this with this. See?
Okay, sir.
So this one is fine. This blue equation is okay. Any questions up to the blue equation? Any questions up to the blue equation?
Up to this is okay, sir.
Up to this? Okay. Now we can do the volume integral of both sides. We can write this, okay? Can write. Fine. Now see here what theorem we can apply with this
Divergence theorem.
divergence theorem. So what does divergence theorem say? Right?
Yes, sir.
So we finally have our result that Yes. Is it okay? This is the final statement of Poynting vector. So this was about the maths part. Let us see the physics part of it. What does this equation mean? Can anybody want to have a try? We did so much of derivation, we got this equation. So what does this equation actually mean? What is E cross H? What could be E cross H? The first thing we see is E cross H. What is E cross H? What will be the direction of E cross H? Can you tell me first of all? E cross H will be the direction of E cross H.
That perpendicular to both E and H.
And what else? What other term is perpendicular to both E and H? What other thing is perpendicular to both E and H? What is the direction of wave propagation? What is the direction of EM wave propagation? It is along E or along H or along something else or plane waves, unguided plane waves. It is sorry.
The direction will be perpendicular to both E and H.
Right? So we can say that E cross H it is the direction of the propagation of the wave. Okay. And what is the unit of E? What is the unit of E?
Unit of
Electric field.
volt.
Volts. Hey, volts. What millivolts? Electric field.
Volt for Coulomb.
No. What is the unit of electric field? This you know, or what we have defined, B equal to, sorry. So what will be the units of B? B of V is volts. So what will be the volts per meter? This is volts per meter. What is H, unit of H? What is units of H?
Weber.
Hmm?
Weber.
No. What is unit of H? What is ampere per meter law? In integral form, what does it say?
The closed surface integral h dot dl equal to
H
I
dot dl
enclosed
equal to what? I enclosed. So what is the unit of I enclosed?
ampere
Amperes. What is the unit of dl?
meter.
So what should be the unit
Meter.
of H? What should be the unit of H?
Ampere per meter.
Ampere.
Ampere per meter.
Okay. So what is, so this is volts ampere by meter square. Now what is volts ampere? What is volts times amp from high school? What is volts times amp?
Ohms.
Right.
Ohm.
Volts by amps. What is volts times amperes?
VA rating.
Hmm? Don't have
VA
to go that much complicated. Volts into amperes. What is the basic unit? There is those things. If I multiply 1 volt into 1 ampere, what we get? 1 watt. Can give the answer actually.
Watts.
1 watt. So this is watts per meter square. Okay. And I am doing this integral over a closed surface. So what will be the total time and total units of the entire left hand side? If I do the surface integral of watts per meter square, what I am going to get?
Sir, what?
Watt. So the unit of the entire left hand side is watts. And watts are the units of what? Which field is
Power.
power. So
Power.
what does this entire thing represent? The relations is the what?
Power of the wave.
A little bit more carefully. Amount. What is this? This is a type of flux, right? This form. See? So it is the total amount of power that is what? Entering the surface or leaving the surface. This is the total amount of power that is entering the surface or leaving the surface. This is power, but this power is the power flux because it has a closed integral of ds. So this is entering the surface or leaving the surface. What it could be. Forget on the right hand side right now. Forget that. What does this left hand side? We will focus on left hand side. So what does this mean? The power is entering the surface.
Leaving.
Why leaving?
Because it's negative.
How it is negative?
Work is done.
Forget. Don't look at the right hand side for the now. Only left hand side. Why it is negative? It is positive, right? Because ds is pointing what? Inside or outside?
Sir,
Sorry? Yes, E and H is what
outside
from?
from the surface.
Sorry?
Outside from the
Outside. So
surface.
this should be E dot H should be outside. So this is the power leaving the surface. Now everything must follow the conservation of energy. If some power is leaving the surface, it has to be coming from somewhere inside the surface, isn't it? You cannot have power from thin air. If it's leaving, some power is leaving going out the surface, it is must be coming from inside something inside the surface. So what from what it is coming? The answer is given. Let us see it in a bit different way. Let us multiply the entire thing with minus 1. What is exactly? right? If you multiply the entire thing with -1, we will get this. So now this, what is this? This is the power. This is the power. Now this will be what? Entering the surface. Now what is happening to that power? That can be explained by these three terms on the right. What is the first one? Let's see the first one. J dot E. See here. What is J? What is J?
The conducting current density.
Conduction current density. Very good. And current density is dimensions of conduction current density as a dimensions of
I by L.
no
Sigma into
sigma into
E.
sigma into E. Yes. What is J? Curl of H equal to J. Okay, assuming that non-varying fields. So what is the dimension of H? This is just now. We discussed just now.
The ampere per meter.
Ampere per meter. So what is the dimension of curl of H? What is curl? It is a derivative with respect to what?
Surface.
What we do with curl? Curl of E is equal to what? Some vector is equal to ijk del x del y del z. So we are deriving with what? Del x. So it will be, this will be ampere per meter square. And what is V? Volts per meter. So what is J dot E? Volts ampere per meter cube. And we are integrating it over the volume. So here we will get. So this is the dimension of volts into amperes or voltage into current. So what is this? What can this represent? What can this represent? What can this represent? Think carefully. Achha, if we have a perfect dielectric, will this term exist or vacuum? Will this term exist?
No, sir.
No. So this term vanishes. But will the other two terms exist? For perfect dielectric or maybe vacuum, will the other two terms exist? Right? This epsilon L del D square dV and the other one D. Will they exist?
Yes, sir, but the
They will
epsilon
exist.
Yes,
will
sir.
Say epsilon will be epsilon. Okay, point taken. So what could this term be? J not E. It is vanishing when there is no sigma. It is not there. What could this be? What could this be? What could this be? अच्छा ठीक है कहाँ where this term exists for what type of materials? in for vacuum and perfect dielectrics, do we have alpha or do we have beta or do we have both? Remember the alpha and beta from the last class? And please mute.
আমি পাগল হয়েছি প্রেমে মাতাল হয়েছি আমি পাগল হয়েছি প্রেমে মাতাল হয়েছি
Who is Sana Khan? Is he from your class? You know him or her?
No, sir, this is not from our class.
Then we can remove him for no point. Remove this guy.
কি হলো কিছু বলছে স্যার?
Okay, so this alpha and beta was where these terms were there in the for vacuum was this alpha and beta was there were there.
The alpha
Sir,
and beta was
for alpha,
Alpha was there or not there? Vacuum
very less.
very less
alpha
or it didn't
wasn't there.
exist. It doesn't exist. So vacuum this
Didn't
this
exist.
was there. For perfect dielectrics, let's see the last day's notes. Where was alpha there? Last classes notes. The idea is that equation is fine, but you understand what exactly this theorem means. Equation is okay. Was alpha there? Last notes for perfect dielectrics.
So for perfect and dielectric, beta was there.
Beta was there, but alpha was not there.
Alpha
But
was there.
for in other dielectrics, lossy dielectrics, both alpha and beta was there. So can there be any relation between this alpha and this thing? Can there be? Is it a coincidence that only this where alpha is existing, only this is existing, and when there is no alpha, there is no this? And what was alpha? Alpha was the
Attenuation.
attenuation coefficient, or the wave power is reducing due to this losses. So what could this J dot E be? Alpha was making the wave attenuate, right? It was like this. If alpha was present, then the wave would have been attenuated like this. So what could this mean? It means a loss in the medium. If some power is entering, a part of that power is getting lost due to heat generation, or the I square are lost, what we had seen in circuit theory. If some power is entering into the surface, partially of part of that power, it might get lost due to this I square are lost or generated and lost as heat. Is it possible? So this term is the so-called I square R loss or heat loss, and it exists for only those materials where there is an alpha or there is a loss coefficient. Okay, For vacuum, there is no loss, so it does not exist. So whatever power is entering the surface, some of them is getting lost as heat. Okay, and this, how much is lost? This amount is given by this term. Is this okay? Any questions? Is it okay?
Yes, sir.
This term is the heat
So,
loss term. Okay, but what amount of power is getting lost? What is happening to the rest of the power? Okay, okay, some of the power is getting lost as heat. What about the rest of the power? They are accounted for this and this. Can you guess what this means? See here, here is a d dt term. Right? Here also there is a d dt term. Okay? Can you observe? Here is a d dt term, here also a d dt term. Now, you tell me, do you know the answer of this question? This is d dt of something that is giving the power. So, what is that something? Think. ddt of what quantity?
energy?
Energy, yes. If we differentiate energy with respect to time, we get power. Agreed?
Yes.
This is be some sort of energy. The remaining term is epsilon. This will be some sort of energy. What sort of energy can this be? And this energy getting stored? This energy is getting stored somewhere. Similarly, this will also be some sort of energy which is stored somewhere else. Agreed? Okay. Ritika, I can't hear you. Okay. So there's some sort of energy. What energy it could be? And this energy is linked with the electric field. Another thing. Do you know something that stores energy from an electric field? In form of electric field, it's related to electric field. And do you know something which stores energy? This is related to magnetic field from your circuit theory things. Can you remember something? Something that stores energy and that is related to electric field. Last energy question. Yes. Can you remember something that used to store some energy and that energy amount of energy was somewhere related to electric field from your circuit theory things? Not clear. Can you remember something that used to store electric field and that electric field was related with somehow can you remember something that is store energy, and that amount of energy was somewhat linked with the electric field from whatever you have studied so far from circuit theory. Can you think of anything? Okay, can you name some things which are used to store energy? Or later use maybe. Can you remember something? Yeah, spring is a very good example. Electronic cell, no. Anything else? Spring is for mechanical energy. We are not interested in mechanical energy. About electrical energy or something similar to a spring. Anyway, spring is a good example. In the electronic cell, actually, the energy is stored in terms of chemical form. So, not that much. Yes, that's a very good. The capacitor, yes. And what was the expression for energy stored in a capacitor? Do you remember anything? The capacitance was C,
CV square.
half CV square, not CV square. See, here also is a half. This cannot be a coincidence. What was C? Let us take the example of simple case. What was C? What a parallel plate capacitor? What is C?
Capacitance.
Yes, capacitance. What is the? Can you tell me what is C? Yes, exactly. See what he has written. Epsilon A into D. Right? See, epsilon also there. We are getting things. But here is E square and here is AD by B square. And it's a dB also. So, what can be done? What is V? E times D. Right? So 1D is cancelling. This is dimensions of what? This is area. This is what? Length. Area into length is what? What is area into length?
Length.
Hmm?
Volume.
So what does this mean? What does this mean? Can you see the similarity? Can you spot the similarity between what this one and this one? We are getting all the terms. Here it is epsilon E square times volume. See here epsilon epsilon E square times integral of integrated over a volume. Right? So what does this term mean? Finally, what could this mean? This term? It is the energy stored. What? It is the energy stored. Can anyone help me with the rest of the thing? Right? Right? It is some energy. So energy is stored what? What type of energy? It is the energy stored in the electric field per unit volume. Right? Do you agree?
Why is it per unit?
Why is it per unit? See here. This energy, what you are getting? These terms were already there, and you are multiplying it with volume to get the energy. Similarly, see here, and I am integrating it to what? dV. If I do the integration, then I get the energy. So what will this be? You remember from Gauss law? What did Gauss law say? Equal to Q enclosed, and we were writing. What was this? What was this? Hmm? Sorry? One more time.
Volume charge density.
Volume charge density. So what will this be? If that is volume charge density, what will this be? Volume energy density, isn't it? If this is volume charge density, then why this should be volume energy density? I mean this term. This term. This term. It should be volume energy density.
Yes,
This
sir.
energy is stored in the
Yes, sir.
electric field. So tell me what should this mean? The other each term?
Energy stored in a magnetic field per unit
Exactly.
volume.
So whatever energy is coming in the surface, whatever power is coming in the surface, some of them is getting lost due to heat. That is given by the E dot J term. The remaining power, what is happening? A part of it is getting stored in the electric field. The remaining part of it is getting stored in the magnetic field. That is clear. That is the Poynting theorem, which is nothing but conservation of energy. Any questions? I don't have time for questions in this session. We will move on to the next session. We will get back to this. Questions we will take in the next session. Okay.